Today we're going through Practical 6, which is for you to eventually write a short scientific paper with the title "The Quantification of the Impact of Indigenous Cultivation on Regrowth of Rainforest." We've worked through in class to define the aim of the work and the objectives. The aim of the study is to compare the impacts of different land management practices used by indigenous peoples on the regrowth of rainforest. The particular objectives are to quantify the impacts of the different cultivation practices on specific areas of forest by direct comparison of recovery in plant cover in two experimental areas. The data shown here at Site A and Site B are those two experimental areas, and this is the observed data showing the recovery in plant community size subsequent to clearance by two different methods. So the first objective is to just make direct comparison between the two sites, but the second objective is to attempt to determine a general mechanism by which these differences are brought about. In order to do this, the records from the different sites are going to be compared to growth predicted by a model. The model that you're going to compare the growth at these two sites to is a model of logistic growth, which again we've been through in class. Now, in order to carry out these two objectives, then we'll just work through what you actually do with the data. So we have two data sets, Site A and Site B, with numbers of plants counted at different times, from a start time of month 0 through, in the case of Site A, to month 45, and Site B actually for a much longer period, through for 120 months. In order to achieve the first objective, then we need to make a comparison between the observed data at Site A and Site B. The clearest way of doing that is by drawing a graph which shows the data, shows the population size change plotted against time. So we'll do a scatter plot. So there's a scatter plot for Site A. And we need to also do the same for Site B. We'll get rid of the title because we want to have a legend rather than a title on the graph. And then we need to make sure that these graphs are actually drawn so as to meet the objective, and the objective is to allow us to compare Site A and Site B, and in order for that comparison to be easily made, we should make sure that the axes are the same. Therefore there's an adjustment required because the x-axis runs to 140 months for Site B and only 50 for Site A. So we need to change the default setting for the axis. For Site A, the scale we need to make run up to 140 rather than to auto scale. Okay, now those two lines can be looked at and compared. The y-axes are the same, they both run up to 700. So that's fine. With those graphs then, with an appropriate figure legend and figure number, which we can then tie into the text, we can achieve the first objective. The second objective is rather more involved, which is to compare the observed data to a model. The equation that we're going to be using to model the growth is the logistic growth equation, which you've been through in class, and it's drawn there at the top of the spreadsheet for you. So that needs to be converted into the notation for Excel, and then that will be entered into a column which we'll call modelled. You can tell from the equation that there's certain parameters in it, k, n0, and little r. We'll keep those parameters separate, so we'll write the equation in here and make absolute reference to the parameters down here, because some of these parameters we're going to change when we go through the process of calibrating the model. So I'll write in a little box here. Can put a box around it, which is going to contain the parameters for the equation. K, n0, and little r. N0 is the simplest one. It's the starting population size, and we can read that from our observed data. And the starting population was 10, so I've written that in there. K is the carrying capacity, which is the size that the population reaches, which it no longer changes. So it's the steady state population size, the carrying capacity, the population that environment can sustain. We can assess what that is by looking at the graphs we've drawn. So for site A, the population does start to level off, but it's real data, so it levels off, but it goes up and down. We know that the population is leveling off at somewhere between maybe 530 and 580 or 600. So we can put a number in there. I've put in 550. It's a number that we can change afterwards when we try and calibrate the model, but it's somewhere within 530, between 530 and 600. We need to do the same for site B. N0 for site B is only 2, and the carrying capacity, well, it's much harder to judge. The population really hasn't levelled off, but we'd have to pick a number again that is perhaps the highest number that was reached, but straight away we've got some inkling that perhaps the model isn't appropriate. However, we can put in a value. We'll say we'll put in 600. So we've got values for k and n0, but we don't have a value for little r. In order to work out little r, we need to consider how we formulated our model of logistic growth. Which we've done in class. The model of logistic growth was a modification of the model for exponential growth. Exponential growth being the simplest model of growth that we could come up with. And that was a model of growth in which the rate of growth depended solely on the population size. So the differential equation for that was dn dt equals little r times n. The integrated form of that equation for exponential growth was n at time t equals n0 times e to the rt. And the logistic form of that is as drawn on here. So we can approach finding little r by actually dealing with the exponential rather than the logistic form of the growth equation, just because it's simpler, and it's appropriate to do so if we consider only the initial part of the growth curve. The initial part of the growth curve, before the logistic function starts to have any effect, will be effectively exponential. So the early months of growth should show themselves as being exponential growth. It's only as you get into the later months of growth that the logistic function will start to limit the amount of growth that's going on. So if we consider the early months, then we would expect to see exponential growth. If we saw exponential growth, we'd expect that the model for it would be n0 times e to the rt. if we want to identify little r from the equation nt equals n naught times e to the rt, then we need to change little r from being an index to actually just being a base number. In order to do that, we take logarithms. So if we take logarithms of both sides of the equation, we get log n at time t on the left hand side equals log n naught plus rt. E to the rt, if we take the natural logarithm e to the rt, it just becomes rt. So we end up with an equation then, log n at time t equals log n naught plus rt. And this is actually equivalent to the equation for a straight line, y equals mx plus c. And the gradient of that line, in the case of y equals mx plus c, the gradient is m. In the case of log nt equals log n naught plus rt, the gradient is of course r. So we can find little r by finding the gradient of log population size during the early stages of growth. So in order to do that, we need a column here which is going to be the natural log of the population size. So we take the natural log of the observed population size, and we can copy that in, and if we plot that on our graph, we'll see that the initial part of the growth appears as a straight line, which indicates that it's exponential. So in order to plot it on there, because these are the logged values, we need to plot them on a separate y-axis. So if we select the data set, we can select the axis, plot it on a secondary axis, and you can see that it is linear, which is the equivalent to exponential growth in the unlogged data. So this is the exponential part of the curve, exponential growth, and it's on logging becomes a straight line. So in order to find the gradient of a straight line, we divide the change in y by the change in x. So down in here, where we define little r, we need to put in the change in y over the change in x. The change in y will be the difference in value between one of these numbers and the one that precedes it. So that's the difference in y, divided by the difference in x will be the corresponding differences in x. X is time, so this one minus preceding that one. Into that, and we get a value of 0.34. Now, you can play with this because this is looking at a difference just between 8 months and 10 months, but you can look at the difference between 3 months and 10 months. Oops. Let's pick that up and drag that up to 3 months. The value of little r changes a little bit. So again, depending on what's taken as being the straight part of this line, the value of little r changes slightly. So again, this value is one that can be altered in order to calibrate the goodness of fit of the model, which is what we will move on to doing. But just at this moment, bear in mind that that value is one that you can alter legitimately by choosing whether you're going to look at the gradient between 3 months and 10 months, or between 0 months and 8 months, and you could assess whether you do that by looking at how straight the line is and which parts straighter than others. So we've got that value in there. We need to do the same for site B. And site B, we can put in the log values. And in the next column we're going to have the modelled. We can copy this. And these we're looking at 7 months and 22 months. Again, you can select where you think the linear part, well, where the exponential part of the growth is, and really in looking at this observed data there isn't really an exponential part of the growth anyway. We can drop on the log data as we've done with the data from site A. We need to make sure again that we plot it on the second axis. Okay. And really there's no linear section. Obviously there's a straight line between the first 2 points, but there's always a straight line between 2 points. If you take the first 3 points, it's not a straight line. So as we work through this process, it becomes more apparent that the model doesn't fit the observed data at site B, but we'll progress anyway. So if we just move the graphs to one side, select both of them, we can move them together. Now we need to enter the equation. We know the parameters, we've got the parameters entered down here, so now we need to enter the equation. So we want to write a formula that's going to equal the modelled value, the modelled population size at a particular time, that time being n0 in this case, and it's equal to k, which we can select from down here. And remember, we're going to copy this equation down, so we want to make an absolute reference to k, an absolute reference to the row number of k. So we need a dollar sign in front of the 28. So that's k multiplied by n0. N0 is that, just below it. Again, if we press F4 twice, we'll end up with a dollar sign in front of the 29. So we've got k times n0. Put a bracket around those two. It's divided by n0 plus k minus n0 times e to the rt. So again, open a bracket, n0 again, b $29 plus k minus n0, okay, minus n0 times e to the rt. So exp is the Excel function. RT, the value of R, take from here, again absolute reference, and times T, and T in this case is number of months, which is 0. And we need one more bracket to finish it off. Okay, and then we can copy that down. model data, drop that onto our graph. It's plotted itself on the secondary axis and we want it on the primary axis. Okay. So the yellow line is the model data, it says in the legend. And the blue line is observed data n. You can see how well they fit. And we can take this equation copy it over here. We just need to then check that it's making reference to the correct parameters, which it is, because we only fixed the row number, so as we move the equation across, all the column numbers updated, and so we can just copy that straight across. That down, and then we can drop the model data. Again, model data has put itself onto the secondary axis, and put it on the primary axis with the observed data, and that's what we end up with. So just by eye, it's not a very good fit. The fit for site A to the model is much better. What we really want now is to be able to have some measure of goodness of fit that's quantitative, and we can then see if we can improve that goodness of fit. If we have a number, we can see if we can improve it by calibrating the model. Calibrating the model would mean changing these parameters, which we could change k, because from our observed data we don't have a fixed value for k. We've got a range for what k might be, and also for little r we don't have a fixed value for little r. There's some error in assessing little r from the observed data, and that's because you can choose the range of the data over which you might select little r. So before we start calibrating, we need to have an idea of a measure of whether we're improving the fit of the model or not. And in order to do that, we are going to use Pearson's product mode correlation coefficient, Corel is the Excel function that we'll use. So in order to use that, we'll have another cell here, which will be our comparison cell. We'll call that modelled versus observed, so modelled versus n, and we're going to use the Corel function. So Corel, and the arguments required are the two data sets that we're correlating with each other. We're going to correlate the observed and the predicted. So we've got the observed and the predicted. Now, if the observed and the predicted were identical to each other, then we'd get a correlation coefficient of 1. So it's a perfect correlation. If it's close to 1, that means we've got a good correlation. We can then play with these parameters in order to try and improve that to make it better than 0.9876. We can do the same. Site B. Site B, the correlation is not as good, which plainly isn't when you look at the data. So we can have a little go at calibrating to see if we can improve the fit then from 0.9876. If we were to, instead of looking at the gradient between 3 months and 10 months in order to define the specific growth rate, if we looked at between 5 and 10 months, it doesn't make very much difference, but it's slightly worse. The fit's slightly worse, so we can revert back to our previous value. And the value of k we've got as 550. If we decided that the value of k was actually a bit lower than that, again, that's not improving. If we make it a bit higher, if we made it 600, that does improve it, so that's 98873, so that's a slight improvement. So this would be a more appropriate parameter to use if we're trying to make a better fit for the model. So you can get a very good fit for site A. Site B, the fit is not as good, and it's apparent really from just a visual inspection of the shape of the observed data that there's no period of exponential growth, and logistic growth leading to a constant population size doesn't occur either. So it's quite different. So to recap then on what you've done, you've compared, you've met the first objective by making a comparison between the population regrowth at two different sites, site A and B. And you've done that by comparing one site with another using a graph, using a scatter plot, and then you've also made a comparison of regrowth at each site with a model of plant regrowth. And in order to do that, you've extracted parameters for your model from the observed data. You've extracted the carrying capacity from the observed data and also the specific growth rate from the observed data.